Memang nak full screen ni. Okay, Assalamualaikum and good morning. So for the second lecture session today, so we will discuss topic on space vector modulation. So I decided to put the SVM inverter chapter for the chapter number 2 because we can have sufficient time lah. Because I want to give assignment for you regarding on this topic, space vector modulation. Okay. So today we discuss on topic 2, chapter number 2. Okay, before we discuss on space vector modulation, I think it is necessary for us to do some revision on sinusoidal pulse width modulation and 6-step inverter. So I believe these two topics you have learned already in subject power electronics for third year subject. Okay, because we can highlight what is the disadvantage of using these two methods. Then we can improve the performance of the output of the inverter by applying the space vector modulation. SVM is the advanced technique, which is widely used in many AC drive applications. Okay. So actually, this is the photo of the three-phase inverter. Hello. So you can notice here the inverter and the photo of the inverter. Here is the heat sink in the black color. Then you can notice here it consists of 6 IGBTs. So you can 6 IGBTs. Sorry. So here 1, 2, 3, 4, 5, and 6, where all the IGBTs attached to the heat sink. So then when the switching operation happen, so then it can transfer the heat efficiently to the heat sink. So then actually the controller, this inverter is flexible to be used for any type of controller. So you can apply using field FPGA and field programming array, DSP, and so on, Arduino. So where you can provide the signal through this socket. So actually this is 10-pin socket. So where this socket obtain the PWM signal from microprocessor digital controller. So then before we connect the signal in order to drive the power switches, so you must insert the gate driver circuit. So this is the gate driver, this part. Gate driver. So each switch or IGBT or MOSFET require one gate driver so that the switch can able to turn on. So actually if the gate driver, the function of the gate driver, it has two. So the first is for amplification, because the signal provided from the controller is not sufficient to drive the power switch to turn on and off the power switch. So then you must have the gate driver to amplify the signal. For example, the controller provide 5 volt or 3.3 volt. In order to turn on the switch, you must step up to 15 volt. Then it must also provide sufficient current. So mean, in other words, you must provide sufficient power level, voltage and current. So another function of the gate driver, so this is the gate driver, gate driver circuit, is for isolation. Because the grounding of the electronics part, which is the sensitive part, your DSP and expensive part, must be isolated with the negative or grounding of the high voltage side. So you cannot connect directly and electrically grounding high voltage to the grounding electronic. So you must isolate the grounding for the 2 points. So that is the purpose of using gate driver. Okay, so actually that one just for knowledge. Maybe we can have a detailed discussion on how to design this part during we prepare for the assignment. Okay, so actually the inverter. So you must know the function of the inverter is the conversion DC to AC. So actually the inverter is the conversion DC to AC, voltage or current, voltage or current. And the inverter can be operated or performed as a voltage source inverter, and the short form is VSI, or current source inverter. And the short form is CSI. And depend on the application. For example, if you want to, and maybe some of you, fourth-year student, have taken the subject modern electrical drive, kan? So when you learn about direct torque control, so you must operate the inverter as a voltage source inverter. So mean your converter operate as a voltage source. But when to run the motor using the field-oriented control, FOC, so the inverter must be operated as current source. For example, for the case of indirect rotor flux oriented control, IRFOC. And so your converter operates as a current source. You control the current. Okay, so actually for the design of the inverter, so actually there are many various types of modulation techniques to control the inverter. You have sinusoidal pulse width modulation, 6-step, SPWM, and so on. So the aim of the control strategy is to obtain high performance. Means the inverter actually aim to obtain high performance. So in terms of maybe you want to produce low THD voltage, low THD, total harmonic distortion. THD stands for total harmonic distortion. Low THD voltage or current. Because, for example, for the grid and connected, and you from the solar or the battery, you convert the DC to AC before you inject to the grid. So you must filter out the unwanted noise or harmonics component. So you must have a clean waveform, purely sine wave shape. Then you can inject to the grid. So means your inverter must capable to produce a very low THD. Because you apply low THD, so mean you can reduce the size of filter. Okay. So another, you must the control strategy aim to have high efficiency, means higher losses, low losses, and also high output power. So mean high voltage and current, output current and output voltage. Okay. So this is the purpose why the researcher shown significant interest to develop various control strategy and modulation techniques in order to improve the performance of the inverter. Okay, so we proceed to the next page. Okay, so here is the standard inverter circuits. So please remember this circuit. So you can notice there are two terminals for the input, okay, where these two terminal inputs are connected to the DC source. For example, output of the rectifier, output of the chopper, fuel cell, and solar panel. And it also has three outputs, A, B, C, where these three terminals are connected to the three-phase load. For example, three-phase AC motor. Okay. induction motor, permanent magnet, brushless DC motor. So this inverter, it also consists 3 legs. So you can notice here there are leg number 1, leg number 2, leg number 3. So where each leg consists of 2 switches, okay? Top and bottom switch. So where switches, top and bottom switches in any leg cannot be turned on at the same time. Clear? That is the restriction of the inverter. You cannot turn on both switches, top and bottom switches, in the same leg at the same time. So for example, if you want to turn on the top switch, Q1, for example, Q1 here, so Q4 must turn off. Otherwise, when you turn on the Q4, Q1 must off, okay, and vice versa. If both switches off, it's okay. That one happen for the case of when the inverter is running for 2-phase conduction. You must differentiate what is the 3-phase conduction and 2-phase. If 3-phase, the switching operation for any leg, top and bottom, must be complementary. And it cannot have same state, on, off, cannot. That one for the 3-phase conduction. But for the 2-phase conduction, it allows one leg of the inverter can be, both switches can be off at the same time. Off is okay, but turn on cannot, because it will provide short circuit. Okay, so you can notice here when Q5 is on, Q2 is on, then you put here is 1000 volt, then it will short, then damage your IGBTs. Okay, in leg 3, Q5 and Q2. Okay, sorry. All right. Okay, then SPWM. So we go do revision for the first technique, sinusoidal pulse width modulation, SPWM. So where in order to produce the output signal, the AC waveform, you must develop or design the PWM control circuit. So where the PWM signal or switching state are responsible to drive the power switches to produce the AC voltage. So this technique, the generation of the switching state is based on the comparison between the modulating signal and a single triangular waveform, or carrier waveform. So where we can write the punya expression switching states for PWM. Sorry, before that, we have to define the switching state at the power switch. Here it will be SA, because in leg number 1, phase A. So for the bottom, because the switching must be complementary, so you must put straight line on top of the letter here. And so mean this, the signal is the inversion of the SA status. So when the top is on, the bottom will be off. SA is 1, logic 1, indicating the switch is on. The bottom switch, SA bar, must 0, logic 0. Indicates that the switch is off. Okay, clear? And for the phase B or leg 2, here will be SB, SB bar, SC, SC bar. Okay, so remember this is the output terminal A, B, C, connect to the 3-phase load. Then you have the input terminal plus to minus. Then you put DC voltage across these 2 terminals. Okay, where the switching states, in general, you can express the switching state as subscript X. So where X can be A, B, or C. So where your XX, SX, it can be either 1 or 0. If SX is 1, meaning that the switch is turned on. Otherwise, 0, switch is off. So SX is 1 if the modulating signal and the corresponding of the modulating signal Vx is larger than or equal to the triangular waveform. Yeah. Otherwise, it will produce 0. So I put just otherwise. So mean if Vx less than triangular waveform. VTRI is the triangular waveform. And so this is the triangular waveform. Triangular waveform. Triangular waveform. Okay. Or maybe we can detail the switching state for the case of SA. SA can be either 1 or 0 if VA and the modulating signal of the phase A, VA, larger than triangular. Otherwise, it will be 0. So maybe I can detail the expression for all switching state. 1, 0 if BB larger than triangular. It will be otherwise. SC if the modulating signal of the C phase voltage, otherwise. Okay, please take note that the modulating signal of the reference signal where VA, VA is the sine function. So you have the peak value Vm. Vm is the peak value of the sine multiplied by sine function. Then you also have VB, same amplitude or peak value, same frequency. But each phase must have different phase by 120 degrees. 2 pi 3. This one positive. Okay. So these three signals, VA, VB, VC, are the modulating signals or reference signal. So you must compare these three signals with a single triangular waveform here. Triangular waveform. Okay, clear? Revision. Warm up. Lihat ni. Okay, so make sure you can relate lah based on these three expression with the model. How to construct this model, the PWM control circuit, using the this equation, three equation, SA, SB, AC. Okay, so VA1 is larger than triangular. If yes, if the condition is fulfilled, then it will produce SA1. For the SA bar, so you must put the NOT gate here in order to invert the signal. Clear? Soalkan sikit. Okay. For running the SPWM three-phase inverter, so this system or circuit we can divide into two parts, and the power circuit and the control part. The power circuit is standard using the standard circuit three-phase inverter. But for the control part, so it based on your control strategy. So for this case, using the first technique, sinusoidal pulse width modulation. Okay. Then this simulation actually is used to describe how to generate the switching state based on the comparison between the modulating signal. For example, this case is VA. VA, here will be VA. Okay, the sine wave waveform is VA. And compared with the triangular waveform. V triangular, V sub TRI. Okay, by comparing these two signals, then you can generate or produce the switching state. Yes, remember the switching state, it can only have two values, either 1 or 0. So means it will produce digital output, digitized output, in order to turn on this, to drive the power switch on and off the power switch. So here is the SA, the switching status for SA. So where the production of the switching status SA is based on this relation. Remember, if SA is larger than, if VA is larger than triangular, for example, maybe we can try to project for this interval, right? This line. For this interval, if you analyze in this interval by comparing between these two signals, the modulating and the triangular, so you can notice that when the VA1 is larger than, the VA is larger than triangular waveform. Okay, because your VA here is larger than triangular. So then your output status SA is 1. Okay. Otherwise, when your, which one? When your, here maybe. So this one is also larger, eh? Here. Okay, clear? So you analyze for this interval here. And so this case, your VA is less than the triangular. So then your status will be 0, logic 0. SS will be 0. Okay. We just revision, yeah. It's okay. Okay, so then by applying this technique, SPWM, then finally you can have the phase voltage here, VAN. The phase voltage VN. So of course, the switching pattern, the wave shape of the VN due to the switching of the switching state SA, SB, and SC. It's not only for the SA. Okay. They combine for all switching state A, B, and C. Then you can have the phase A voltage, VAN. Clear? Division ini. Okay, so where the fundamental component, the fundamental frequency of the output is the same as that of the reference wave, and the amplitude of the output is determined by the relative amplitude of ratio. So you must know how to calculate the fundamental component. So maybe I put VA, 1. 1 refer to the fundamental component. Okay? Or you can write as V1. So you can calculate V1 as a multiplication between the modulation index, you multiply by VDC divided by 2, half of VDC. So MI is the modulation index, where MI is the modulation index, where modulation index MI is equal to, actually MI is the ratio between the peak of modulating signal. So remember, the peak of modulating signal is VM, and VM divided by peak of triangular. Okay. So please refer equation that I provide here. Which one? This. Okay, so you notice here is the VM, the peak of the modulating signal. VM. These three signals we consider as a balanced waveform. balanced voltage waveform, because they have same amplitude, same peak value, same frequency, but they must have different in phase by 120 degrees. Okay. Okay, so actually in order to control the inverter using this technique, sinusoidal pulse width modulation, so you can apply two control parameters. So the first control parameters is modulation index. Actually, you control MI, you control modulation index, you can obtain the desired fundamental component V1. You control MI. Okay. So another control parameter is modulation ratio, MR. Here, MR. Okay. So the purpose of using MR, actually you can adjust the location of the harmonics. Okay, harmonics. For example, if I sketch the frequency response, the spectrum component of the output voltage, sorry, spectrum component. So maybe we can put y-axis is the voltage harmonics component. So y-axis and the x-axis is the frequency. It's not the time, frequency. So the first components is actually the fundamental component here. Okay. So where the height or the amplitude is defined as V1, sorry, V1. It's not VM, V1. The fundamental component, V1, here. Where you can control the fundamental component by controlling the modulation index, MI. Yeah. You control MI. But to adjust the location of harmonics, maybe I sketch with green color here. So this is the nearest harmonic, nearest to the fundamental component. Okay? So maybe I define this one as the nearest harmonic. The nearest harmonics. Okay. So actually you can adjust the location by controlling MR. Normally F1, sorry, this one F1 is the fundamental. So if you refer to this equation, the F1 is the fundamental component. Practically we set at a constant value like 50 Hz, because you want to inject your output waveform to the grid system, 50 Hz. But the only frequency that you can change is you adjust the triangular frequency, FTRI. Triangular frequency. So actually the triangular frequency, it will determine the inverter switching frequency. Your inverter switching frequency. For example, we set at 10 kilo, 50 kilo. Depends on your type of power switches. For example, IGBT, you can set 50 kilo. But for the MOSFET, maybe you can set beyond than 100K Hertz, 100 kilohertz. So by adjusting or set at higher triangular frequency or higher MR, so actually you can push your nearest harmonic to be located far away from the fundamental component. For example, here you said, okay, sorry, the fundamental is 50 Hertz, right? But the nearest harmonic now you can push at higher frequency, very high frequency. For example, 50 kilohertz. Okay, by set appropriately the value of MR. You can set proper value of MR. So why is the reason? you set the nearest harmonic at high frequencies. Because of what? Can anyone give answer? Sebut nama. Okay, because of you want to reduce the size of filter. Okay. When you set your nearest harmonic to be located at high frequency, for example, 100K, 50K, so then you can design very small filter by choosing very low cut-off frequency. When you apply low cut-off, your size filter inductor capacitor will be reduced. So that is the reason why we have to set the location of the nearest harmonic at high frequencies. Be clear? Right. Then next page, simulation. So maybe I need to open MATLAB first. MATLAB. Okay. Open the MATLAB. Here is the MATLAB software. Where's the file? SPWM. Okay, let me demonstrate what is the effect if we change the value of two control parameters, MI and MR. MI, modulation index and modulation ratio. Okay, open. So this is the simulation model. Okay, so actually you can notice there are two parts here. The power inverter. So where the output of the inverter is connected to the passive load, just R load only. I just put purely resistive load. And here is the control part, the PWM circuit. So you can see here to generate the switching state SA, B, and C based on comparison between these three signals, A, B, C, VA, VB, VC, and a single triangular waveform. So VA, VB, VC is the sine function where the amplitude I set 1, frequency 50 Hz, but you must put in radian per second because the unit is omega, it's not F. So actually same amplitude here, but this B phase, it has phase different by 120. This one may be lag by 120. Here will be lead by 120. Okay. And then we compare with the triangular to produce the switching state. So this case, I set the amplitude is 1. Here also 1. A, B, C is 1. And the triangular also 1. So actually this triangular, it will produce amplitude is 1. Where it will vary between 1 to -1. 1 to -1. And the frequency here, maybe I put 500 first. Because we want to see clearly effect and the comparison between the modulating signal and the triangular. So that's why I put very low frequency here. So and then I can simulate. Okay, sorry. Before that, the DC voltage I set 100 volt. And the battery voltage 100 volt, the input of the inverter. And then we can run the simulation. Okay. So then you can see the result from the scope here. Oh, go to the first monitor. Okay. So the first graph actually plot the waveform of the triangular and the modulating signals. So you can see here. And sorry, the second graph, the output waveform. So this case, I do not plot the switching state. I just straightforward plot the output waveform. Okay. So this is the output waveform of the phase A. For example, this one is for the phase A because I just measure for the phase A voltage. Okay. No B or C. So this case, I put the voltage measurement across to the load. Okay. Positive here, minus, and the voltage measurement must be connected in parallel. Then this voltage measurement provide the information of the voltage VAN, and here VAN, the signal will go here. VAN, same label. Okay. So that's why you can this scope can plot the phase voltage VAN. Okay, then here will be what? Okay, so this scope is used to plot the first graph to plot the graph of the modulating signal VA and the triangular. Second graph, the switching state. So then you can verify what we have discussed. The switching state, it can be either 1 and 0. It will produce 1 here. For example, this interval 1, logic 1, if the VAN, so the VA is larger than triangular. Otherwise, when here, for example, this point and this interval, the blue color is less than the triangular, right? So that's why the status will be 0. Okay, this is just to verify that what we have discussed. Okay, here, this is the phase voltage. Okay, then to see the frequency spectrum of the output voltage, so you can use power GUI block here. Power GUI. Power GUI stands for Power Graphic User Interface. Graphic User Interface. So you double click this block, then go to the Tools tab, and go to the FFT analysis. Then you can choose the waveform and the phase voltage because we want to plot the frequency spectrum of the phase voltage. Okay, so I just analyzed for 2 cycles, starting from 0.01 second. So that's why I set here start time is 0.01 second for 2 cycles. So then you can see 1 and 2 until to 0.05. And so remember the fundamental frequency or the frequency of the modulating signal, I set 50 Hz. And 50 Hz, 2 pi L, 2 pi 50. So that's why your period will be, what is the period? Inversion of the frequency, right? 1 divided by 50, you get 0.02. Okay. So that's why it can plot, sorry, this signal will be analyzed for 2 cycles, starting from 0.01 to 0.05. Okay. So there's 0.01, you add up with the 0.04, then you get 0.05. Okay. Okay, then to plot the frequency spectrum, just click the display button. Okay, click the display button, then you can see the fundamental component here, which is located at 50 Hz. So actually, this is the 50 Hz. My mouse cursor, where this axis, F frequency axis is 50 Hz. So this is the fundamental component, V1, fundamental component, V1. And the amplitude value is almost 50. Why 50? Because you said your MI is, the motion index is 1. So remember, equation. So you have this equation, right? V1 MI VDC divided by 2. Your MI is 1. Because MI is the ratio between the peak of modulating signal, right? Peak of modulating signal divided by peak of triangular. Your V1, VM is 1. Where is this mentioned? Here. You said your amplitude is 1. And the triangular waveform also 1 here. And the amplitude is 1. But it varies between 1 to -1. And peak to peak is 2. But for the peak value is 1. Clear? So 1 divided by 1. Okay? 1 divided by 1. Here will be 1. Here also 1. Then you get 1. VDC is, you said VDC what? 100 volt. Just now, yeah. VDC 100 volt. Then you can calculate V1 as 100 divided by 2. Then you get 50 volt. Okay. Clear? Tahun 4 okey lah kan. Tahun 3. For third year student kan. So maybe this one something new for you lah. Okay, so let's say you want to obtain the desired voltage is what? The V1 desired now is you want to set 25 volt. So what actually control parameter that you want to adjust? Of course, MI, right? MI. So this case, in order to get V1 is 25 volt. So your MI, you have VDC is constant, 100 volt. Okay? Here will be 100 divided by 2. Then you rearrange the equation to calculate the required MI. Right? You rearrange the equation MI to calculate the required MI. So from here, 25 times 2 divided by 100. Then you get what? 0.5. Clear? So in order to get V1 25 volt, so then you need to adjust the MI. So you refer this equation. So remember, please do not change the value of peak of triangular. So you must set constant value of peak of triangle. So the term that you can change is VM. So in this case, VM you must set 0.5. Yeah, 0.5. Here you change the value from 1 to 0.5. Here also 0.5. There. Okay. All three modern signals have same amplitude of 0.5 volt. Okay. Then you need to run the simulation again. Okay, completely run. Then we can see the frequency spectrum. Okay. Now you can see the fundamental at 50 Hz is 25 volt. So maybe I can. So this is the fundamental component located at 50 Hz. So where the value is 25 volt. Okay, so you see, by controlling the first control parameter, MI, so you can adjust the fundamental component, V1. Okay. So how about to adjust the location of harmonics? Okay. From this result, you can notice here, the nearest harmonic is here, this one. How to remove the data tip. Cannot remove it. Okay, so this is the nearest harmonic. So in order to minimize or reduce the size of filter, so you must push the nearest harmonic to be located at high frequencies. Because this case, the triangular frequency I said is 500 Hertz. 500 Hertz. The triangular frequency, 500 Hertz. Okay. So we look back at this triangular. Because this block designed the triangular wave shape. And the triangular frequency will determine the inverter switching frequency. Okay. So in order to increase the switching frequency, so this case maybe I can set 5K lah, 5K. Okay, 5K. Normally in practice, we can set larger than this, maybe 50 kilo. So 5K. So we can see the effect by applying a larger frequency. Tools, FFT analysis, display. Now you can see the nearest harmonic now is located at 5K. So you push the harmonics to be located at higher frequency. So then we can minimize the size of filter. So that is the purpose. Why in practice we prefer to set higher inverter switching frequency in order to minimize the size of filter. All right, V5K. Normally we set at 10K or 50K. Okay, so then we can minimize greatly the filter size. Okay, so now you have seen what is the effect by adjusting two control meters, modulation index and also the modulation ratio. Modulation index is used to adjust the fundamental component. Modulation ratio is used to adjust the location of the harmonics. Okay, okay, clear. Apa lagi ni? 6 step. Revision, still revision. Okay. For the 6 step, so you apply the same topology circuit. It consists of 6 IGBTs and 3 legs. The switching cannot be turned on at the same both top and bottom cannot turn on at the same time for any leg. But the wave shape, so you can refer to this waveform, 6-step waveform. So here is the VEN. So this is the VEN voltage, phase A voltage, phase B voltage, and phase C. So it will have 6 steps for one complete cycle of the waveform. So one complete, starting from here, maybe go to here. So you can have 6 steps. 1, 2, 3, 4, 5, 6. One complete cycle, you can have 6 intervals, 6 change of the wave shape in staircase of the waveform. Same goes for the other phases, VBN and VCN. It will produce same frequency, same amplitude, but different in phase. VN starting at 0 degrees. For B phase, it has delay by 120 degrees. Then phase C, 240. Okay, by applying the 6-step, you can produce the 6-step voltage by generating appropriate switching state. The advantage of using this technique is it can produce the maximum output voltage. This technique, it will produce the maximum output voltage, but it suffers for the harmonic distortion, higher THD, total harmonic distortion, because of the square wave shape, 6-step wave shape. You cannot applying this technique for the grid system. You want to sell your energy, you design your inverter, you want to sell to the utility company and TMB, you inject to the grid using this wave shape, 6-step, because it will distort the grid waveform due to the 6-step waveform, because this 6-step waveform consists of higher harmonics component. Before you want to inject, you must put filter so that you can have purely sine wave shape waveform. Then you can inject to the grid. Okay. Okay, so to calculate the harmonic component, you can apply this equation. This equation. Or actually, from this equation, you can calculate the fundamental component. We interested for this topic to calculate the fundamental component. Just now, you can calculate the fundamental component using the SPWM. SPWM. WM. Is it right? SP apa tadi? Then, for the sixth step, to calculate the fundamental component, V1 kan? So you just substitute the value n is 1 using this equation. Nampak? You get n1 kan? You substitute n1. Then you get what? 2 VDC divide by 3 times n1. So mean 3 pi, right? Then in the bracket term here, you have 2 plus cos n also 1. You just substitute 1 because for fundamental component, n is 1. So here you set n1, here also 1. Yeah. And n is 1. Then you get what? Here will be, someone calculate cos. So actually you get, for the term bracket, you get 3, I think, 3. Then someone verify using calculator. Cos pi per 3, what? Cos apa? 180 bagi 3. Cos 60. Cos 60 degrees. Then you minus with cos 120 degrees, right? Clear? So then actually you can calculate V1 as 2 VDC divided by pi. Is it right? Clear? 2 VDC divided by pi. So clearly this equation shows that the fundamental component produced from the sixth step is larger than that produced from the sinusoidal pulse width modulation. Yeah, because for SPWM, V1 SPWM, the maximum possible voltage can be produced is half of VDC. So remember you have MI, VDC divided by 2, where your MI is 1. So the maximum voltage is 0.5 VDC. So this is for the sinusoidal pulse width modulation. But by using the 6-step technique, then you can produce voltage larger than that. And kalau you try to simplify this equation, then you get what? 2 divided by pi. 2 divided by pi, what the value? What is the value? 2 divided by shift pi. Battery tak ada. 0.6 something, right? 0.64. 0.64 VDC. So where the value is larger than 0.5 VDC. Okay. Simulation. Okay. Simulation for the 6th step. Yeah, this one. Same inverter circuit, same load, same DC voltage, 100 volt, same DC voltage, same load, but the control part is different. In this case, I using the pulse generator block to design the switching state for SA, here for the SA, here SA, SB, and AC. So where the signal is varies between 1 and 0. I double click this block. So you can see the amplitude is set 1. Period is 150. Pulse width is 50%. Delay is 0. Here delay is 0. This one same amplitude, same period. Pulse width same, but delay is 1/3. 1/3 of the cycle, 50 Hz. Okay. So same goes for here. Okay. So actually you can design the switching state waveform by referring this waveform. So please refer this waveform. If you understand on how to sketch the waveform, so then there will be no problem for you to construct the simulation model. And you just refer to this graph, the waveform. Okay. So you can notice for the SA, B, and C, pulse width is 50%. Means the on time and off time are same. 50%, right? 50%. So they vary between 1 and 0. Then you can it must have for one phase to another phase, it has a delay. So you can refer to this waveform. Okay lah, this is just a revision. I don't want to take much time to discuss in detail for here, because this one you have learned already in last time, last semester or last year. Mana ni? Here. Okay, then we try to verify the output. Is it improved? The DC voltage is set 100 volt. So then we can run the simulation. So this is the switching state waveform. Okay. So actually we firstly, before you want to construct completely, you can design only for the switching state circuit first. Because you want to verify your setting. Is it okay or not? Your setting of your pulse generator. Then you compare with the waveform from the lecture notes. Okay, then the output of the waveform here. That is the output of the three-phase waveform. Okay. Same wave shape, same amplitude, same frequency, but each phase must have different phase by 120 degrees to each other. Okay. Okay, now we can see what is the fundamental component by analyzing through the FFT analysis. FFT analysis. Okay, then you can click the display button here. So then you get the fundamental here is 64. Correct? So means 0.64, you multiply by 100, then you get 64 volt. Okay, 64 volt. Sorry. 64 volt. Okay. So where the production of the output voltage using the 6-step voltage is larger than that produced in sinusoidal pulse width modulation. Right? Okay, simulations I've shown already here, comparison. So actually we can conclude by analyzing by analyzing the two frequency spectrum of the output voltage obtained from these two techniques, SPWM and 6 steps. Here is the SPWM, SPWM, and 6 step. So then we can conclude that the maximum of fundamental component of output voltage. Output voltage. So for the V1 here, SPWM is, we know that MI VDC divided by 2. So here we set MI is 1. We want to get the maximum possible. So then you must choose MI is 1. So then from here, 1 multiplied by 100 divided by 2. So then you get 50 volt. 50 volt here. Here is 50 volt. Okay. So this is the waveform. So this is the component. The straight line. Here is the fundamental component, V1. But for the 6th step, V1 subscript 1, comma 6th step is, so we obtain the equation as V2 VDC divided by pi. So from VDC as same for both method, because we want to have a fair comparison. So you must apply same DC voltage, input voltage, same load. Okay. So from here, 2 multiplied by 100 divided by pi, then you get berapa? 200 divided by shift pi. 63.67 lah. 63.7 volts. Okay. This one 64. Okay lah. Almost similar right, to the result, to the calculated value. Okay. So we can verify or conclude that the production of the output voltage, specifically the fundamental component, will be larger in the case of the 6-step technique. Because in SVM, actually, we want to improve the voltage. So that is why I highlight the comparison of the fundamental using these two methods, SPWM and 6-step. So by using SVM, we can improve further the fundamental component. So actually, the maximum is produced by the 6-step. Okay, clear? So then, okay, maybe we can have a break for 10 minutes before we proceed to the new topic, space vector modulation. Any question so far? Tak ada. Berapa dah? 12. Tak okay? Hmm. Lambat lah dia. Okay, we continue our discussion to the new topic, space vector modulation. Okay, boleh? So space vector modulation, short form is SVM. Okay. So before we discuss detail how to design the control algorithm or the modulator of space vector, so it is necessary for you to understand the definition of the space vector. The definition of the space vector. In Malay, we call it vector ruang. Vector ruang. Okay, so where the space vector, so this is the equation. So this is the standard equation. So V. So for the vector unit, you must put bar. For my class, you don't need to bold. Other textbook maybe designated the space vector with the bold letter. Right? For our class, so make sure you put straight line in order to define this unit is the vector. This unit is not vector. It's not the scalar control. It's not the scalar unit. It's the vector unit. So where the V to third, so you have open bracket here. Okay, for fourth year ni revision. So I believe this topic have covered. You have learned already in modern electrical drive. So this is the standard equation. So maybe I put this equation is equation number 5. Before that, maybe 4. So okay lah. So where the 2/3 here, 2 divided by 3 here, so we can call it, this is as a scaling factor, and this is the scaling factor. Scaling factor. So the space vector V, and the voltage space vector, we can also rewrite the equation as, and by writing the equation into rectangular form, so which is VD plus JVQ, right? Rectangular form. You have real and imaginary part. Real and imaginary part. So this equation, another equation, we define it as, we put number as equation 6. Okay, where A, and so you can notice here you have this one A and also A power of 2 ni, A squared. So where the unit vector A, okay, unit vector A, so this is the unit vector because you have the straight line on top of the letter. So where the unit vector A has amplitude 1 and the angle is 120 degrees. Yeah. And for A squared, same amplitude 1, but the angle is apa? 240 degrees. Yeah, 240 degrees. So you can write this equation for unit vector in polar form, and because you have magnitude and angle, and you can rewrite this equation into exponential form. So where e power of j 2 pi divided by 3, or maybe you can put ej 120 degrees. It's okay. 2 pi per 3 in radian. Okay. Or ej 4 pi divided by 3. Okay, you times 2, right? 120, you times 2, you get 240 degrees, or 4 pi per 3 radian. Okay, so where maybe I put here A is a unit vector. It dilarang bercakap. It can be expressed into a rectangular form. So how to rewrite the unit vector A in rectangular form? So you can write into rectangular form by applying what? Euler theorem. Euler's theorem. So where in this theorem, if you have Ej theta, so you can transform it from the exponential form to the rectangular, cos theta plus j sin theta. Okay. So means here Ej 2 pi per 3, applying Euler theorem, you just substitute in 2 pi per 3 plus j. Okay. And you can solve for the cos 2 pi 3 is minus half plus j. So this is equation number 7. Hey, come on. Then for the power of 2 here, Ej then minus. Okay, this is equation number 8. For unit vector A and A power of 2, they have same real part, right? Minus half. Same magnitude for the imaginary part. but different in sign, because you set 3 divided by 2 for the a power of 2 is minus j, so 3 divided by 2. Okay, so actually you can sketch the vector component for unit vector of A. So let's say here is okay, good. So this is the D axis, right? You have D and Q axis. Okay, then you have 3 components. So the one is the real part here is 1. So where the 1 is the factorized for the VAN. For VBN, unit vector of A, so you must have here this component of vector, right? So this vector is A. Okay. And for the VCN, the factor term here is here, A power of 2. So this is the origin. So maybe this one, where the imaginary part, sorry, this is what value here? Set 3 divided by 2, right? Okay. And for the A power of 2, this is minus set 3 divided by 2. And the real part for the unit vector A and A power of 2 are same, which is minus half. Clear? So then by referring to the equation 7 and 8, actually the different angle between unit vector A and 1 is 120 degrees. So same goes to the unit vector power of 2. Okay. There. Okay, so you have equation 7 and 8. So where these two equations express the unit vector A and A power of 2 into a rectangular form. Rectangular form. Sebab dia ada A plus JB. A, JB. Okay. So you starting from, you express the unit vector into polar form, exponential form. Then you must know how to write the equation into a rectangular form by applying Euler's theorem. Alright. Lagi. Then, tak habis lagi. Then you have to substitute. Sorry. Okay. This equation, substitute. Substitute the rectangular form of unit vector A into 5. Okay. So where is the equation number 5 here? Okay. The original equation 5. Okay, so you apply this equation, then you substitute A. Okay. In terms of you write into rectangular form into this equation. Okay, so let me, so this is equation number 5. I rewrite again. So V is V 2/3 is the scaling factor. Okay. So now you can substitute the unit vector A and A power of 2. So where your A is what? Minus half. Okay. So the first term bracket here is unit vector of A. Here will be power of 2. Okay. Okay, then you try to expand this equation, expand and you separate this equation into two parts, real and imaginary part. So actually then you can write the equation as Dn okay. Okay. Okay, you expand this the equation above, then you try to split this equation into two parts, and you have real part and imaginary part. Okay. So you notice here there is J here. So then maybe you can try to simplify further this equation first. So yeah, 2/3 Bn of Bn. So actually for the second plus J, you can factorize it. 30 divided by 2, put outside the bracket, then try to reduce so that you can obtain the equation as that BBN minus ECN. Yeah. So then we know that the space vector you can also define as BD plus J BQ. So by comparing these two equations, actually you can obtain the equation for VD and VQ. Therefore, the voltage space vector component VD is and VQ okay. So this is question number 9 and 10. Betul, macam mana dia dari 9, 10 ni? Boleh, 2, 7, 8, okay. 7, 8, 9, 10. Alright. Okay. So make sure you know how the process to derive the space, the voltage space vector component VDVQ. Starting from the equation here, equation number 5. Okay. So you must apply Euler theorem in order to write the unit vector A into rectangular form. Then you substitute the unit vector A into equation 5. Then you try to expand this equation and split this equation into two parts, real and imaginary part. Then you compare with this equation here. Then finally you can get the equation of VD and PQ. Boleh? Soalan final itu masa ni. Oh iya ke? Dah lupa. So maybe for this subject, it's not ni lah cover for your final lah. To test your derivation. Understand how to derive the equation. Okay, any question? Third year student. Okay. Apa? Apa dia tunjuk? Okay, then next page. Simulation result. So actually, after that I will demonstrate the transformation, how we can transform from the three phase quantities VAN, VBN, VCN, then you can transform into two phase. Means you get the waveform of VD and VQ. Here will be VD and VQ. VQ. The yellow color is VQ. Okay. Then after you get these two waveform VD and VQ, then actually you can plot the space vector. How it can actually you can plot the space vector on DQ plate using the XY graph. For a balanced system, since our three phase VA, VB, VC are balanced, so means same amplitude, same frequency. So actually the space vector, it will form a circular locus where the circular shape is centered at origin. And so you can notice here is the DQ axis, then the origin is here. And the circular locus is centered at origin. Okay. So let me open the file first. Where is the file? MATLAB. So I think space phaser. Okay, so from this simulation model, so actually I tried to design the three phase waveform, VA, VB, VC, using the sine wave block. So then this signal will pass to this section. So you can see XAN in general representation, X can be voltage, current, or flux. So for our case, it's voltage because we work on space vector, voltage. So the voltage here, three phase voltage, VAN, VBN, VCN, then you can construct this transformation block in order to plot the waveform of the DQ, VD and VQ. So actually you can construct this model based on the equation that we have discussed. Yeah. Sorry, this equation 9 and 10. So by applying these two equations, you can construct the model of the simulation. Yeah. So maybe you can compare. Is it same? Okay. So here is VD. Here is VD. My mouse cursor is VD. Then you can try to understand lah. By applying this equation, then you can construct using the suitable simulating block. So this is the sum add block, gain block to model the 2/3 here. This factor 2/3. Then you have VAN, the bracket term here, VAN minus VBN half, by 2, VCN divided by 2. Then you can see here is the gain, VBN, you multiply by 0.5. Divide by 2 lah. Here also VCN divided by 2. But then here is the bracket term actually, right? Okay. Output of the add block. This is the add block. This output is the bracket term of equation 9. Is it right? Bracket term, eh? Then you multiply by 2/3. Then you can plot for the VD here. Okay, clear? Then for VQ, here, VQ. So you can apply equation 10. So you can try to construct the bracket term here, the difference between the VBN and VCN. Here VBN minus VCN. So this is the bracket term, VBN minus VCN. Then you multiply by 1 divided by 3. Square root of 3. Sorry, square root of 3. Yeah. Okay, so then you can plot the waveform of the DQ voltage using this scope. And so actually this scope, here I'm using the scope to plot the waveforms. So this scope consists of 2 graphs. So the first graph we plot the phase voltage, VAN, VBN, and VCN. And the second graph, the bottom graph, plot the waveform of VD and VQ. And another scope here is the XY graph. It's not the normal scope. That scope plot the waveform, for example, voltage versus time, current versus time. But this one plot XY mode. For example, VD versus VQ. VQ is Y-axis. Your VD is set as a X-axis. Okay. And then we can run the simulation. So this is the, maybe I need to resize the window first. Minta sini. And the waveform. Okay. Oh yeah, sorry. This is the waveform. We try to relate the relationship between the 3-phase and 2-phase, and from the 2-phase to plot the locus. Okay. Okay, I run the simulation again. Okay, you can see that I continue to run. So actually you can see the space vector, it form a circular locus. So where the vector is rotating counterclockwise. It depends on the sequence of the phase voltage. Okay. There. So you can have a circular shape centered at origin. Where the radial component of the locus is 1. 1 kan? Because you set the amplitude of the phase voltage VN, BNCN for this case is 1. So let's say I try to change the sequence of the voltage. So this case, the locus plot to form a circular locus where it rotates in counterclockwise. Counterclockwise. Because your sequence, VM come first, then followed by VBN, the yellow color, and VCN, blue color. But for the VD-VQ, the VD come first, then followed by VQ. So that's why your space vector rotate in counterclockwise. So let me change. Okay, now let me change. Now the VBN here will be positive. Okay. And for the VCN, this will be negative. Change to negative. So we swap 2-phase, VB and VC. So means VA come first, still VA come first, then followed by VCN. Then finally followed by VBN. Okay. So we try to simulate. Okay, so you can see your space vector is rotate in opposite direction. So now rotate in clockwise. Okay. So you can also notice here the VD and VQ waveform where the yellow come first. So mean the VQ come first. Right. Just now before this VD. Yeah. But this case VQ. Yeah. Then followed by VD. It is to demonstrate and to verify the equation that we have derived just now. Okay, any question? Okay, so far so good. Slow and steady. All right, so simulation pass. Then we go to exercise. I've been exercise. Okay, so for a given instantaneous value of phase voltage at time Tx, so at time Tx, so you can get the instantaneous value, nilai ketika. Determine the voltage space vector and identify at which sector V is located. Ini just for exercise lah. Okay, so you need to identify at which sector the V is located. So based on the waveform, actually it provide the information of the instantaneous value. So from there you can calculate VD, right? VD and VQ. So I rewrite the equation VAN, VBN half, VCN half. Then from here we just substitute VAN and VBN and VCN. So your VN is 0.866, VBN is 0, VCN. So since the value, instantaneous value is negative. Okay, simple. Then you can solve the value of VD is 0.866 volt. Okay, for VQ, 1 divided by SET3, VN minus VCN. Zero minus 0.866. Okay. So from the waveform, please take note that the red color is the VAN, the yellow is VBN, the blue color waveform is VCN. Okay. So then from there you can get the instantaneous value of the phase voltage. Then you substitute into equation, VD and VQ equation. Here VQ is 0.5. Okay, where your D is positive, your Q also positive. Right? VD and VQ are positive value. So mean you can expect the space vector is located in the first quadrant. Quadrant one, So you have DQ plane, you have 4 quadrants. So since the D and Q are positive, so mean the space vector located in quadrant number 1, first quadrant. Positive. So is it either sector 1 or sector 2? So in order to get the answer ataupun ni, you must calculate the angle. Okay, angle. So where your angle you can calculate as tangent, arctangent here. Okay, VQ divided by VD. 0.5. So the angle is what? 30 degrees. So from here, we can say that the space vector is located in sector 1. Sector 1. And because from this diagram, actually the space vector, we know that the space vector form a circular locus. So where we can divide into 6 sectors, 6 sectors, which is equally divide by 60 degrees. So mean all the sector have same size, 6 sector have same size angle. So mean the angle different here is 60 degrees, right? So mean since your angle, your calculated angle is 30 degrees. So this is your space vector. Okay. So where the angle here is 30 degrees. So based on the calculated value, the angle is 30 degrees. So then we can identify the location of the space vector, which is located at sector 1. Located in sector 1. Okay, simple. Still warm up. Warm up. Okay, lagi ni. Apa ni? Alright. Then any question? So I think we can end our class now. So maybe we can proceed for the rest topic. Mapping vector, derivation of the vector component in terms of the switching state, and for the next week. Okay. So for tomorrow, don't forget group number 2. So bring your laptop. Make sure install with MATLAB. At least 2020 version. Newer is better. Okay, see you tomorrow. Bye-bye. Hey, stop. Okay. Ni keluar. Eh? Oh, stop recording.